Hello, everyone. How are we doing? Welcome to today's session on radiation. So we're going to be covering the two types of beta radiation and also alpha and gamma radiation. And we're going to be talking a bit about their dangers and their uses as well. So can everyone see and hear me okay? Hey, Mariam, how's it going? Hey, Melon. How are you all doing? Well done as always for getting signing up to do some physics on a Sunday afternoon. Hey, Magdalena. Hey, Brazen. Yeah, good afternoon to you as well. But yeah, seriously good effort. Hey, Karen. So I hope that today can be useful for you guys. I don't know if you guys have seen much stuff about the different types of radiation before. So this is going to be A level, but some of this you might have seen at GCSE, depending on your exam board. But we'll be going a bit beyond what you'd see at GCSE. Okay. Right, I think we should get started. So cheers for coming, everyone. As I said, really good effort to come see physics on a Sunday. It's about me. So my name is Matt. I'm head of physics here at SatRevise, currently a PhD student, kind of doing physics, but doing it undercover in the computer science department. And I've been tutoring A-level physics for the last 4 years, including quite a while at SatRevise now. Hey, Monkey Mania. Hey, how's it going? All right. So right now, we're going to be doing a web class. And there's going to be, we've got some prepared slides that I'm going to go through with you, and I'll ask you various questions along the way to check that we're all on the right track and we're all understanding what's going on. We're doing a lot more of these sessions on the SatRevise website. And for 1 week, you can get a free trial where you can access these tutorials. So keep a note of this code. We'll show it again at the end as well. And you can see more of these classes on our website. All right. So what's our objectives today? We're going to try and understand how and why radioactive decay occurs. We're going to mainly think about the how. The why is a bit of a funny one. We're going to analyze the properties of the three radiation types. So there's alpha, beta, and gamma, two types of beta. And we're going to understand the practical applications of radiation. Okay. So maybe this isn't what we already know, but this is the stuff that we're going to kind of, roughly speaking, be aware of for today's session. So the first thing we're going to need to know about is nuclear notation. So this is the notation that we use to describe the nucleus of some atom. There's three symbols here. There's this number at the top left, number at the bottom left, and there's a symbol here. For example, we might have something like lithium. I don't know what the actual numbers for lithium are. I don't know, 32, 7 or something. So it's this kind of symbol. So can anyone tell me what the number at the top represents? What's this number here, which we've called A? Similarly, can anyone tell me what this number at the bottom Z represents? And what this symbol X is? Well, I'll say now the symbol X is what we call the kind of element symbol. It just tells us which element that we're talking about. For example, we might be talking about lithium or oxygen. So these are the kind of symbols that you see in the periodic table. Good. So we have a kind of mass number or nucleon number at the top. So I'm going to call it nucleon number, but mass number is also perfectly fine. Good. It tells us the number of nucleons. Okay. Good. And then we have this number at the bottom, which is the number of protons and that's often called the atomic number. And that's because the number of protons is the number that tells you which atom it is that you're really actually talking about. Okay, great. So the second thing we're going to need to know about is conservation laws. So when we have subatomic particles, so let's say we have some kind of an atom. Atoms are typically made of three types of things. There's things called protons and neutrons that make up a nucleus in the middle. And around the outside, we have things called electrons whizzing around. Okay. So these are kind of subatomic particles. They all live inside atoms, and they can all interact with each other. When they do, they satisfy certain conservation laws. There's certain numbers that have to be preserved during a reaction. So the first number, which is always conserved, is charge. So let's say I tell you that this reaction at the top here occurs. This is a proton, an electron, a neutron, and something called an electron neutrino, which we'll talk a bit more about later. So if I tell you this reaction can occur, then that means that the charge must be conserved. So let's look at the charge of each particle and check that the charge is the same before as it is afterwards. So what's the charge of a proton? The charge of a proton is +1. Let's write that down here, actually. The charge of an electron is -1. So on the left-hand side of the reaction, we have a total charge of 0. On the right-hand side, we have a neutron, which has a charge of 0. And then we have an electron neutrino, which we'll mention later as well, happens to have a charge of 0. So this charge number is indeed conserved here. Good. There's a couple of other numbers, which I think it'd be nice to be aware of for today, although we won't use them too explicitly. Okay. So baryon number. Baryon number. This is a second number that's conserved. And essentially baryons is a kind of hood that we can put protons and neutrons and everything else under all together. So proton will have a baryon number of +1. An electron number will have a baryon number of 0. And neutrons will also have a baryon number of 1, and electron neutrinos, a baryon number of 0. Essentially, what's happening here is the baryon number pretty much keeps track of how much mass is going on. So later on, we're just going to look at atoms, and we're going to look at a conservation of mass rule. So I'll go into more detail about that then. And there's a third number called lepton number, which again, I won't say too much about other than just to make you aware of it. There's actually a third number that's being preserved in this reaction. Protons have lepton number of 0. Electrons have a lepton number of 1. Neutrons have a lepton number of 0. And this is where these electron neutrinos come in handy, because so far they were 0 for everything. They didn't really matter. But here they let us balance this lepton number equation. So that's a kind of primer on stuff about subatomic particles. Now we're going to go back to the start again. I'll mention what spec points we're going to go through, depending on what exam board you're on, and we will learn properly about each of the 3 types of radiation. Okay, so these are the AQA spec points we're going through. Okay, the OCR spec points and the EdXL spec points we're going through. All right, so part 1, nuclear decay. So essentially, we have atoms. Atoms have these particles on the inside that make up the nucleus, and stuff going around the outside as well, like electrons. We're going to talk about how the nucleus, the bit in the middle, can decay, usually emitting something or absorbing something so that the nucleus itself changes. And this is called radiation or radioactive decay. So the first example we're going to look at is the idea of beta decay, and in particular, beta minus decay. So we'll say what it is in words, but it will probably actually be easier to digest in a formula. So we'll do that afterwards. So beta minus decay, if you know what it is, feel free to race me and put it in the chat as well. So what is beta minus decay? Beta minus decay is when a neutron emits an electron and an anti-electron neutrino. So I'll explain what that is. Sounds complicated in words. To become a proton. So we have a neutron, it wants to become a proton. Now here's the thing, a neutron has a charge of 0, but a proton has a charge of 1. So we need to somehow balance the charge. So what it does is it also emits an electron, because by emitting an electron, we now have a charge of -1, and now the charge is balanced on either side. So a neutron has to emit an electron if it wants to also make a proton. So here we go, neutron becomes a proton, but we also need to produce an electron at the same time. Now the problem is there's this lepton number conservation thing as well, and essentially we've created an electron from nowhere, and electrons have to be balanced out due to a different conservation law. So there's an extra thing going on called an anti-electron neutrino, which we draw like this. The V symbol means it's a neutrino, and the bar means it's an anti-neutrino, which means it's kind of like the opposite to a neutrino. Okay, so this is the equation that describes beta minus decay, and it's one of the most fundamental decays that can happen in a nucleus. So let's say this is just like the equation for an individual neutron inside a nucleus. Let's imagine that we're looking at the entire nucleus now that has one of these neutrons decay. Then we can describe this in terms of the symbols we were writing down before. So let's say I have an atom and it has a neutron, and that neutron becomes a proton. Can anyone tell me what they think happens to the number A, the mass number? So we're going to get a new element here. It's going to have a new number here, a new number here. We're also going to produce one of these electrons and this anti-electron neutrino. But can anyone tell me what this number A is going to be here? It's the number of nucleons we have, the number of protons and neutrons all together. Before we had A particles in our nucleus. So we started with whatever the number A is. Maybe A is, but whatever A is before, A is just how many particles we have in our nucleus. And that's not going to change, because maybe we start off, let me draw something like this, for example. So here's a beta decay. I've got some random nucleus here. It's got 5 particles, so A is equal to 5 here. Now, when we have a beta minus decay, one of these neutrons becomes a proton. So I'm drawing the protons as the kind of filled in circles here. There we go. But the number of particles hasn't changed, and that's all A was there for. So the number A doesn't change. What does change is the number of protons, which is this bottom number here. We have one more proton after the decay than we did before. So this number here goes from Z to Z plus 1. So this here is the general equation for nuclear decay of some nucleus. Greetings, nice to meet you. Okay, so now we're going to look at essentially the opposite of beta decay, which is beta plus decay. Okay, so beta plus decay is the opposite. This time we're going to have a proton, which is going to try and become a neutron instead. Okay, so beta plus decay is when a proton emits a positron and an electron neutrino to become a neutron. Okay, so this time we start with a proton, and now we get a neutron, but we had a +1 charge over here. So we need to somehow make sure we still have a +1 charge on the right-hand side. Well, positrons, the opposite of an electron, a positron has a charge of +1. So that's why the proton needs to also emit a positron. But again, there's this lepton number thing going on, and essentially that means we have to have one of these neutrinos to balance out this electron, this positron, sorry. And it turns out that the one we need is called the electron neutrino. Okay, so if we try and write this in terms of an equation for an entire nucleus, again, we've got a proton becoming a neutron. What happens to this number A, do we think? We're going to get some new atom here, Y, with a new number up here. What's that number going to be? We've had a proton in the nucleus become a neutron. What's happened to the total number of all protons and neutrons altogether? Absolutely right, it hasn't changed. That top number just says, how many particles do you have in your nucleus if you add up all the protons and neutrons together? Well, we haven't changed the number of protons and neutrons altogether. We've just changed one of the protons into a neutron. So this number A is going to be the same. What's going to happen to the number Z? Well, Z is the number of protons. We've lost a proton because it's become a neutron. So Z becomes Z minus 1. Good, absolutely right. Really nice one, Matthew. Okay, great. So I would say that beta decay is the most complicated of the radioactive decays. Yeah, nice present. Well done. The other two are kind of on the extremes, alpha and gamma decay. So gamma is the easiest to think about, so we'll start with alpha. Alpha decay is when an alpha, and we'll have to explain what this is, an alpha particle is breaks off, let's say. Breaks off from a nucleus. So what is an alpha particle? An alpha particle is a very special type of small nucleus, if you like. It's made of 2 protons and 2 neutrons. So alpha particle is 2 protons plus 2 neutrons, all in one big particle. Okay, so let's say I start with some element with A nucleons and Z protons, and let's say it emits an alpha particle. So we're going to get some new Y, and we're going to get an alpha particle, which has taken away 4 particles overall. 2 of them were protons. So what's the number at the top for Y going to be here? Y has lost 4 particles and it's lost 2 protons. Well, this top number here is just the number of neutrons and protons altogether. Well, we've lost 4. So this is going to be A minus 4. How many protons have we lost? Well, we've lost 2. So we're going to go from Z to Z minus 2. And you might notice that always the numbers on the left-hand side of the arrow are the same as the numbers on the right-hand side of the arrow. On the right-hand side, we have A minus 4 and 4. Altogether, that adds up to A. And that's exactly what we have on the left-hand side. Similarly, we have Z minus 2 and 2, which adds up to Z, which is what we have on the left-hand side. Good, A minus 4, really nice. Now, the easiest decay to think about is gamma decay. And that's because the only thing that really gets emitted is energy. So gamma decay is when a nucleus releases excess energy by emitting a gamma photon. And this word gamma here essentially just means really high energy, really high frequency. So it's a really high frequency photon. Okay, so in terms of writing an equation for this, this is a really nice and simple one. So we'll use the Greek symbol for the letter gamma. And then, okay, a gamma decay is given by, well, we have some nucleus. We'll have the same nucleus afterwards. It's just lost some energy in terms of this gamma photon, which we write at the end. So this is the nicest equation to write down. We don't have to keep track of any numbers. Okay. So now we're going to talk about the causes of decay, or at least the conditions under which decay is going to occur. So first of all, we're going to ask, why would alpha decay happen? Why would it be that I have some nucleus and it just decides to get rid of 4 of its particles? Well, one way of thinking about it is that essentially there are certain numbers of protons and neutrons that you can have together which are stable. That's actually given by this line here, which we'll explain in more detail in a second, this red line. So there are certain ratios of protons and neutrons which are stable. It turns out if you just have too many protons and neutrons, it's impossible for your atom to be stable. So alpha decay happens simply when there are too many nucleons. Now, when I say stable here, what I essentially mean is, can the nuclear force, which is the thing that attracts all of these nucleons together, can the nuclear force actually be strong enough to hold everything together? If you have too many nucleons, it's essentially too much to be kept together by the nuclear force. So alpha decay happens when there are too many nucleons to be held together by the nuclear force. Don't worry if you haven't heard of the nuclear force before. That essentially be the only mention of it. But that's why alpha decay happens. And so essentially alpha decay happens for all of these particles up here. So here we've got a graph of number of neutrons against number of protons. And every dot on this graph is a certain element that has been found. But there are certain ones which have lots of neutrons and lots of protons. So they'll be up here on the graph. And all of those are unstable, and all of those will undergo alpha decay, getting rid of some of their protons and neutrons to try and move towards more stable areas. Okay. Now, not only is just having too many particles a problem, having an imbalance of particles is also a problem. And that's where beta decay happens in, because beta decay is all about trading protons for neutrons or vice versa. So beta decay happens because there is an imbalance between the proton and neutron numbers. Okay, so for example, if I'm too far on this side of the graph, that means I have essentially too many neutrons and not enough protons. So I can move back towards the middle here by going through some beta decays, getting rid of some of my neutrons and trading them for protons. Similarly, I can go the other way as well, using beta plus decays instead. Okay, so how's everyone feeling? We will have 2 exam questions we can look at about this stuff as well. So yeah, just pop in the chat to let me know if this is making sense. There's a 1 or 2, or if you're struggling with it, the number 3. Let me know if you have any questions. One, nice. Absolutely no worries if it's not a 1 or 2, because we will go through a couple of questions. Awesome. Okay, that's looking really nice. Well, let's have a go at some of these exam questions. This is a really nice one, actually. So 1A, the lead nuclide, lead-210, is unstable and decays in 3 stages through alpha and beta emissions to a different lead nuclide. The position of these lead nuclides on a grid of neutron number against proton number is shown below. So this is exactly the kind of graph or a snippet of the graph that we were looking at before. On the grid, draw 3 arrows to represent one possible decay route. Label each arrow with the decay taking place. Okay, so how does this work? We have to figure out what the different types of decay do to us on this graph. Let's say we start at the top here. They're asking us to come up with 3 decays, which take us to this point here. So first of all, let's figure out what alpha decays do. If this particle goes through an alpha decay, what happens? Well, it loses 2 neutrons and it loses 2 protons. So what does that mean? Well, our neutron number, which is this one here, should go down by 2. And our proton number should also go down by 2. So went down from 128 to 126, and we'll go down from 82 to 80. We lose 2 of each. So we should end up here. So if we do an alpha decay, we end up here. So now we've got 2 decays left. How do we get to here? Well, what do I need to do? I need to gain 2 protons and lose 2 neutrons. How can I lose a neutron and gain a proton? That's beta minus decay. So if I do a beta minus decay, that would take me to here. I'd lose a neutron and gain a proton. If I do another, that'll get me to the right place. So we've managed to draw on the graph 3 decays we need to get from the start to the finish. So it's a really nice question. Let me know if you have any questions about that. Now, the next question is more of a formula type one. Complete the following equation to show the beta minus decay of protactinium. I always struggle to say that one. Okay. So beta minus decay, what happens? Well, we produce a beta minus particle. That's another way of writing the electron. And what's the other thing we produce? We produce an electron, an anti-electron neutrino. Now we have to try and fill in these numbers here. So let's take a look. The number on the bottom here essentially represents charge. We'll mention that in a second, but let's first think about the top number. So with the top number, we have a particle that has a mass of 233. It's got 233 nucleons in it. And neither of these have got any nucleons in them. So actually, this is going to be 233 as well. Now, we're going to have to talk about a trick for the bottom number. So for the bottom number, what happens in beta minus decay? When beta minus decay, a neutron became a proton. So here we've got 92 protons, and that's after beta minus decay. So beforehand, we must have had 91. Because in beta minus decay, we would gain a proton. Good, really nice. So the top number is the same, but the bottom number has changed. Okay, let's look at another. This is a really good question, actually, 1C. So the isotope, radon-222, decays sequentially by emitting alpha particles and beta particles, eventually forming the isotope lead-206. 4 alpha particles are emitted in the sequence. Calculate the number of beta particles in a sequence. Okay, so let's first see what the result of emitting all those alpha particles would be. Well, if we start with Rn 22286, and then we emit 4 alpha particles, 4 lots of alpha, well, 4 here and 2 here. What happened to our proton number or atomic number? Well, we started with 84 protons, and then we went through 4 alpha decays. Each alpha decay takes away 2 protons. So altogether, in 4 alpha decays, we'll lose 4 lots of 2 protons. In other words, we'll lose 8 protons. So that will take us, sorry, we started with 86 here. So that will take us to 78 protons. Now they say some beta decays are going to happen. And those beta decays need to take us from a proton number of 78 to the proton number of lead. And the proton number of lead is 82. So how do we get from 78 to 82? Well, each time we do a beta decay, we'll gain a proton. To get from 78 to 82, we need to do 4 decays. We need to gain 4 protons. So since 82 minus 78 equals 4, there will be 4 beta minus decays. Great. 4, absolutely right. Really nice. Cool. Okay, so that was essentially the technical half of this session. We introduced all the technical definitions. We worked with some formulas. And now we're going to do kind of the conceptual part where we compare kind of features of these different types of radiation. So this is the application section. So we have 3 types of radiation here. We're just going to talk about beta minus radiation for now. So we've got alpha, beta minus, and gamma. And they all have very different properties. First of all, they each get different distances in air. Let's say I have some source emitting alpha radiation. I can ask, how far can that radiation get before it essentially decays away and you wouldn't notice it? So for alpha radiation, alpha can get to about 10 centimeters away from the source. So it has a range of up to 10 centimeters. Now, depending on your exam board, because these numbers are kind of estimates, you might have slightly different numbers. So it's probably worth checking your own textbooks. But these are roughly correct at least. For beta radiation, well, beta radiation can get further, and that's the main point. It can get up to about 1 meter. So that's a factor of 10 further. Now, gamma radiation can essentially get as far as you like. It essentially never dies. So it has what we call infinite range. So if you're far away from a radioactive source, the main type of radiation you really need to be worried about is gamma radiation. Alpha and beta probably won't reach. Okay, now we can think about how we test for these different types of radiation. And the key point here is going to be that some of these particles have charge and some of them don't. That matters because when charges move through magnetic fields, they get deflected, they start to turn around. So let me ask you, charges have, when they go through magnetic fields, they end up turning, they end up being deflected. So will alpha radiation be deflected in a magnetic field? In other words, does alpha radiation have a charge? So maybe to answer this, it does have a charge. Absolutely right. Why does it have a charge? Well, it's made of 2 things. Neutrons, which don't have any charge, but it's also made of protons. It's got 2 protons in it, and protons are positively charged. So it will be deflected like a positive charge. Beta minus radiation, well, that's an electron. An electron has a minus charge, a negative charge. So beta minus radiation will be deflected like a negative charge. So this is really great news, because if you're trying to test for what kind of radiation is being emitted by a source, if it deflects the way you know a negative charge should, and that's something you can find out beforehand, then you know straight away that you're dealing with beta minus radiation. So this is really powerful. Now, gamma radiation is just a photon, and photons don't have any charge, so there will be no deflection. So again, if your radiation being emitted isn't being deflected by a magnetic field, you know what you're dealing with is gamma radiation. Okay, so now we can think about absorption. And there's a couple of reasons why you care about absorption. One of them is safety, if you're trying to block the effect of some kind of radiation. It is indeed A-level. There will be stuff in here that you would have seen in GCSE, but certainly there'll be new stuff as well, yeah. Okay, so alpha radiation can be absorbed by paper. Beta radiation can be absorbed by a thin sheet of aluminium. Yeah, or wool. And gamma radiation, it's harder. Again, just like how it doesn't ever really die in air, like it's hard to properly block gamma radiation, but you can certainly decrease it by putting a load of thick lead in the way. So it's the hardest to block out. So just decreased by thick lead. So gamma is really hard to deal with in this sense. Finally, there's ionization. So ionization is essentially a measure of the kind of damage that an individual bit of radiation can do. So here's the idea. Let's say I have this alpha particle moving along. So this is some alpha radiation here. And let's say I have some atom. Maybe this is an atom in my body. So it might have an important function. Here's all the particles it's made of. And then this alpha radiation comes crashing through and it bumps into the electron. When it bumps into the electron, it kicks the electron away. So now what I'm left with? I'm just left with whatever atom I had before, but with one less electron. And that can really change its behavior. It can change its function in my body or in wherever it is. And so that can be some kind of damage. And we call this process, because it takes an atom, gets rid of an electron and turns it into an ion, we call this ionization. Now, alpha, being this big, heavy particle, is strongly ionizing, meaning that when it bumps into an atom, it is the one most likely to do some damage. Beta radiation is kind of medium. It's made of an electron, so it has some weight to it, but not a lot. And then gamma is made of photons. And that's the least likely to really actually interact with some kind of electron in an atom. So that's weakly ionizing. So there's this weird trade-off. Alpha is the most damaging when it hits something, but the less likely to reach it. Yeah, so gamma is the least ionizing. And that's essentially why it has the longest range, because it's less likely to bump into something and get stopped. Alpha has such a short range, kind of because it's so likely to bump into something and then get stopped and knocked off its path. So there's this kind of trade-off between how dangerous something is when it hits something and how likely it is to reach you. Okay, so what are these dangers of radiation? Well, because it can edit and change the structure of an atom, it can damage or kill living cells. Living cells. So that's a serious issue that we need to try and avoid. In particular, it can also damage DNA, which is a certain type of cell. or collection of cells. And this can cause the growth of cancers. So we certainly want to try and avoid this. So how can we protect ourselves against these damaging features of radiation? Well, first of all, we learned that these different types of radiation can be blocked by different types of materials up to a point. So we should store all our sources in case they're emitting gamma. We should store all of our sources in thick lead containers. So store in thick lead containers. You kind of don't need that much to stop alpha, depending on how much there is, but better safe than sorry. And if you've got gamma, you really want the thick lead. Okay, now again, we don't want to handle them directly. Only handle with gloves / tongs. Anything that increases the distance between our human bodies and the dangerous radioactive source is good news. So use gloves, use tongs, or even better, use some kind of robot or machine and control it from a distance. Yeah, nice. Finally, just spend as little time as possible around the source. So just reduce exposure time as much as possible. We can never entirely remove our exposure from radiation. We can try and reduce it as much as possible. Okay, so these are the dangers, but radiation isn't all bad. It has some uses. So why do we even handle radiation? Well, the first thing they can be used to do is observe fluid flow patterns. So let me mention this here. Fluid flow patterns. Radioactive material, you put it inside some kind of fluid that's going to float, and you're not going to be able to look at the fluid. Maybe it's in a pipe, maybe it's in a human body. It could be water in a pipe, it could be blood going through the human body. Either way, you can't look at it directly. But if you put some radiation in or something, then you can track how this thing moves kind of behind the screen that you can't see. So, and the idea is because radioactivity, if it's gamma radiation, for example, it can actually get out of whatever surface it's trapped behind and be detected. Okay, so let's say we use a tracer on a person. We want to check how some material is moving around the human body. So we put a bit of radioactive material in. Well, we don't want to cause any damage. So we should use weakly ionizing sources. So when we use radioactive tracers on people, we should use weakly ionizing sources. Sadly, I won't get much chance to talk about quarks today. Sorry about that. Okay, which also don't stay radioactive for a long time. We want radioactive sources that don't stay radioactive forever, where they could be causing damage. We want them to stop after a day or two once we've used them to trace something. Okay, there's some other applications. Testing thickness of materials. And that's because, for example, beta radiation, it can get through really thin aluminium, but not ever so slightly thicker aluminium. So if you want to check how thick your aluminium is, just put a detector to the other side and check how much beta radiation is getting through. Yeah, absolutely right. You can use alpha particles for smoke detectors, that's true. Another one is detecting cracks in pipes. Again, the story here, it's whenever you can't look at the thing directly, a crack in a pipe, that's going to be stuck behind some wall. So detecting cracks in pipes. Because it's stuck behind some wall that you don't want to have to break open, you need to be able to detect stuff through the wall. And that's where you can use radiation. Yeah, this is A2. Is this AS or A2? That's a good question. I will just check. Let me just check the spec points. For AQA, it looks like it depends. At AS level, you need to know about alpha, beta, gamma decay. But then in A level, you seem to need to know about more of the applications and be able to talk about beta plus decay as well. So it's a kind of mix of AS and A level in general, I expect. To be sure, I would just check your textbooks to see where this comes up, because it's going to depend on what exam board you're on. All right, finally, killing cancer cells. So sure, radioactivity can cause cancers. Okay, sure. Hopefully you learned something anyway. All right, so radioactivity can cause cancers, but also because radioactivity can kill cells, you can aim radiation at harmful cells like cancer cells and try and use the radiation to actually kill those problematic cells. And in that way, you can actually treat cancers with radiation as well. And that's what radiotherapy is. All right, so we got a couple of questions. First of all, how confident is everyone feeling? Even if this didn't turn out to be the the right bit of the course for you. All right, nice. Again, as always, no problem if it's not a one. And if you've got any questions, let me know. All right. So, state which type of radiation, alpha, beta, or gamma, produces the greatest number of ion pairs per millimeter in air. So this is a really roundabout way of saying which type of radiation is the most ionizing, which one creates the most ions as it passes through a millimeter of air. Well, we said that alpha was the most ionizing. So the answer here is going to be alpha. Then they ask which one could be used to test for cracks in metal pipes. So here's the idea. Maybe I've got the ground. I've got some pipe here that's got some crack in it where everything's leaking out. I can't see because here's my eye here. I can't see through the ground. I need something that can get through all this dirt in the ground. So the point is that, for example, gamma radiation, when you ask how it makes them visible, it doesn't make them visible in the sense that I can't actually see this radiation. But what I can do is I can put a detector here that detects gamma radiation. And because gamma radiation is kind of penetrating enough that it can get through the ground, we can actually detect it, even though it's around here, behind the surface of the ground. Okay. So here we need something that can get through the ground and reach our detector. So that's going to be gamma radiation. Okay. Specific radioisotope sources are chosen for tracing the passage of particular substances through the human body. Why is a gamma emitting source commonly used? So we've got the human body. Okay, this is a terrible drawing of the human body, but it doesn't matter. And we're trying to watch the passage of stuff as it goes through the body. And so we got some kind of radiation coming from here that we need to detect. Well, we need it to pass through the skin so we can detect it. So we need it to be gamma. There's another good thing about it being gamma, which is gamma is the least ionizing. So kind of for the same reason, it's less likely to do damage to our internal organs it's more likely to pass through them to the outside. So gamma is least ionizing, so is safer, causing less damage to the body. It's exactly right. It's because it's the least ionizing. Really nice. Now, there's a second advantage you could have mentioned here if you wanted, which is that also gamma will be the easiest to kind of get outside the body, again, because it's the least ionizing. So it's the easiest to detect as well. All right. So last question. State and explain 2 precautions that should be taken when working with a sample of magnesium in a school laboratory. So a bit of context for this question. In earlier parts of the question, they've mentioned that magnesium is going to produce radiation. So really what they're asking is, what precautions should you take when dealing with a sample that produces radiation? Well, we said the sample should be kept in a lead container and only handled with gloves / tongs. Those can be some really nice marks to get in the exam, actually. Yeah, use tongs and gloves. Really nice, well done. Finally, discuss which of the 2 types of radiation, beta minus or gamma, would be the most hazardous. Okay, so this is quite an interesting question because beta is more ionizing, but it's less likely to reach you. And here, so if this source of radiation was inside the body, the most ionizing is the most dangerous because it's most likely to crash into your internal organs and cause damage. Outside of the body, well, it's less likely to reach you and do any damage. Whereas gamma, maybe it's less ionizing, but it is more likely to actually reach you. So a small sample outside of the body that you're handling, the gamma is actually more hazardous. So gamma, because of its greater range in air, so it's more likely to reach you. Hopefully that makes sense. Feel free to ask more questions if that answer doesn't make sense. In the meantime, you should now be able to understand how and why radioactive decay occurs, analyze the properties of these 3 or kind of 3.5 radiation types, and talk about their applications and also their dangers. Okay, so thanks very much for coming to the session. And thanks for all the engagement in the chat. It's actually really handy because it helps me see how everyone's getting on. Feel free to ask me any questions you have. In the meantime, so yeah, let me just pop that there. Feel free to ask me any questions. Greatest range in air. So maybe I'm handling some sample of radiation. The beta radiation will get, maybe a meter and then it kind of dies out. Whereas the gamma radiation can go as far as it likes. And so it could be a hazard to people, even if they're far away. That's the problem. So it has a greater range. Gamma has a greater range in air, and that's why it will be hazardous. Okay, so I just want to let you know about a couple of things. Gamma is used to kill cancer, true. There's upcoming web classes, and you can see them on the schedule here. So these are the ones online. But also, I just want to show you and remind you that you can come along to some of our sessions on the SatRevise website for free. So we have a code that we sent off at the start, which I'll put back here as well. Yeah, finally some chemistry sessions too. Yep. But on SatRevise, and for the next week, you can come to the sessions for free. You sign up and you can get a 7-day free trial. We're doing 4 or so, at least, classes like this a week. And there's going to be 2 types, which I'll mention in a second. So I'm just going to take you around the SatRevise website in case you want to join us this week. So here we go. Just going to start my share a second. Okay, great. Here we go. All right, so hopefully you can see the SatRevise website. I'm not sure if it works on the app, actually. We might be able to check that in time for you. I'm actually not sure. Okay, so I'm on the SatRevise website. And let's say I want to access the tutoring resources. Well, okay, I'm going to go into tutoring. And, well, I like physics, so I'm going to take a look at the physics stuff. And if you come here, then you'll be able to go to more classes like this, but on the SatRevise website, ones that won't be on YouTube. So the idea of what we're doing on SatRevise is to do essentially the idea of having kind of private tuition, but to make it more accessible and affordable. So our idea is to charge a fixed rate of about £50 a month, although you can get 7 days free as a free trial right now. And we have 2 types of classes going on. We have web classes, which are more structured like this, where I go through some specific prepared content where you can ask me questions and I'll ask you questions as well, and we'll try and get through the stuff together. And then we have more flexible sessions. In the more flexible sessions, which we call drop-ins, you can just come into the session with a question you're struggling with or something you don't understand, and we will try and understand it together. I will try and provide you with an answer. And that's really almost more like a kind of a tuition session, if you like, a kind of group tuition. So we have the drop-ins and the web classes, and they work really nicely together. So here's a clip from when my hair got a bit messier in the middle of lockdown. And here's the schedule for what's coming up. So let's see where we are. So we're just coming up to the 26th. So we've got magnetic fields, elastic conditions. As you can see, we're doing year 12 and year 13. And here's one of these drop-in sessions where you can just come in and ask anything you like. So, great. And I also just want to let you know about the following. So we have some new resources, which is we have set up some new revision cards that you can access. So this is a separate thing. And these are pretty handy cards. Here's the idea. We've gone through every single specification point. So in principle, all of the principles that you could be asked about in your exam, all of the key ideas in your course. And we've put them all onto revision cards. So this is already handy. This is concise. It's a nice way to revise. But the key stuff happens on the other side of these cards. So you can read about a couple of things. You can learn a couple of things about photons here. We've got the key formulas going on. And then you can look at the back straight after and check you actually digested this stuff by looking at these, at the backs of these cards, where we have some questions that you can try and answer to check your understanding. So there's a handy new resource we've got, so feel free to check those out as well. All right, so thanks very much, everyone, for coming. I hope that was useful. Again, thanks everyone for coming. That was a really great session on my end. So yeah, thanks for making that so fun. And hopefully see some of you on SatRevise. Remember, you've got a 1-week free trial, and here's the code. So it'd be really nice to see some of you there. And in the meantime, just cheers for coming. And yeah, let me know if you have any questions. All right, cheers for coming, everyone. Does it expire? I think it will expire at the end of the week. Yeah, so it'll give you a week. Maybe it's a week from now, I'm not sure, or a week from when you use it. I'm actually not sure. Let me see if there was any questions here. Does it work on the app? Not quite sure. Gamma used to kill cancer, yeah. Yeah, so Sissy, if you're still there, just to mention, the greater range is a greater range in air. And because gamma radiation has a greater range in air, it's more likely to reach you, more likely to get through your skin to the internal organs and cause some damage. So that's why kind of outside of the body, the gamma radiation was the biggest hazard, the biggest cause for concern. All right, thanks very much for coming, everyone. And I don't think there's any other questions. So hopefully see you all at the next web class and enjoy the rest of your Sunday. All right, thanks for coming, everyone. Bye.